In this video, I will explain what Masked Authenticated Messaging is. IOTA is specifically developed for Internet of Things or machine-to-machine economy. IoT devices will generate a huge amount of data which can be stored on the Tangle. These IoT devices can broadcast data using different types of wireless technology such as Wi-Fi, Bluetooth, LoRa, ZigBee, etc. For example, a LoRa sensor node can measure temperature, humidity, magnetic fields, moisture, etc. In this example, this node measures the temperature. This LoRa node transmits sensor data to a receiver, also called LoRa gateway. The distance between node and gateway can be several kilometers. The LoRa gateway is connected to the internet and sends data to a server. This server is running a Node.js Masked Authenticated Messaging application, which in turn sends sensor data to the Tangle. These are the sensor data stored on the Tangle. Masked Authenticated Messaging means the message is encrypted. Another word for it is mask. The message is confirmed to be coming from the device, meaning it is authenticated. A continuous message stream is created on the Tangle and will carry on until the device stops publishing the data. This is also called messaging. Masked Authenticated Messaging is a module built on top of IOTA that makes it possible to send messages fully encrypted from authenticated parties. IOTA Masked Authenticated Messaging, MEM for short, makes it possible for sensors and other devices to encrypt entire message streams and securely store those in the Tangle, each on a separate address. Only authorized parties will be able to read and reconstruct the entire message stream. In essence, it works a lot like a radio, where only those with the right frequency can listen in. In MEM, only those with the right channel IDs get access to the message. Sensor data is published to the Tangle on the channel ID ABC. To receive the sensor data from the Tangle, you need to subscribe to channel ID ABC. IOTA uses the gossip protocol to propagate messages through the network. Messages are gossiped through the network. You know how gossip works. Alice hears a gossip. She tells this gossip to all her close friends. These are her close friends. And these friends tell the gossip to their close friends. This node, for example, will tell the gossip to its close friends, these two close friends, and so on and so on. Bob publishes sensor data to the Tangle on the channel ID ABC. These are its sensor data. Alice is interested in Bob's sensor data and subscribes to his channel ID ABC. When a message with channel ID ABC reaches Alice's node, she will be notified. These are Bob's temperature data. Messages from Charlie broadcasted on the channel ID DEF will be ignored by Alice. A short simplified explanation how the MEM stream works. In a Masked Authenticated Messaging stream or message chain, every message holds a reference to the next message. This is message 0, 1, 2, and 3. Message 0 holds the reference TTP to the next message, TTP. Message 1 holds the reference AAB to the next message. Message 2 holds a reference to the next message, and so on. The message stream only flows one direction. A subscriber with a channel ID, for example, address AAB, has no access to the upstream messages, these messages. In a Masked Authenticated Messaging stream, the message is encrypted, also known as mask, and the message also contains a signature. As you can see over here, the data is encrypted and the message also contains a signature. The data is encrypted and the message also contains a signature, etc. The signature proves that the publisher created the message. Here are some interesting points to remember. The channel ID is also called the root. The message is attached to the Tangle using this root. When the message is attached to the Tangle, the transaction does not need to be confirmed. After a snapshot, all messages are deleted from the Tangle. The messages are still available if the subscriber is connected to a permanode. I have created a simple Masked Authenticated Messaging demo. This is the link. This is the IOTA Masked Authenticated Messaging demo. This demo uses the MEM JavaScript library mem.web.js for web applications. For Node.js applications, use the mem.node.js library. Both libraries can be found at this location. Click on this link. Use this library for web applications and use this library for Node.js applications. The MEM JavaScript library publishes transactions to the Tangle that contain only messages with no value. Please note the following. The MEM JavaScript library is a work in progress and may have some breaking changes in the future. These will most likely be minor in addition to extending functionality. To install the Masked Authenticated Messaging demo, view the HTML source code. This is the HTML page. View the source code and read the installation instructions. Get this IOTA library from this link. Get this mem.web.js library and this WebAssembly file from this link. Both files are located in the library folder. Copy this HTML file, the IOTA library, the mem.web.js file, and the WebAssembly file to a web server. Let's assume your web server has this folder structure. Here's the HTML file, here's the IOTA library file, the mem.web.js file, and here's the WebAssembly file. Next, modify the HTML file and enter the correct path corresponding to your situation, and also edit the mem.web.js file. In the mem.web.js file, search for the WebAssembly file and enter the correct path according to your situation. It must be an absolute path starting from your web server doc root. This demo uses the mem.web.js library because I'm using it in a web application. More information about the MEM client JS APIs can be found at this location. And here are the APIs. For example, init, change mode, create, etc. A short description of each API can be found in this table. I will not explain these APIs. Please pause this video and read the description for its usage. And here is the rest of the APIs. The MEM API implementation can be found in this file. Here's the init. Here's the subscribe, change mode, create, etc. The MEM client.js library is a wrapper library which uses this WebAssembly file. WebAssembly is a new binary format for executing code on the web. Rust is a programming language similar to C++. Emscripten is a source-to-source compiler which can also produce WebAssembly. The Rust compiler with Emscripten support uses Rust programs as input and outputs WebAssembly files. In this example, the iota-bindings-emscripten.webassembly file. The MEM client.js library uses this WebAssembly file and can be run in a browser. The MEM client.js library uses the following Rust modules. These two Rust modules. The bindings between the MEM client.js library and the Rust modules can be found in the bindings folders. These binding folders. The actual Rust implementations can be found in the other folders. For example, this is the MEM Rust module. These are the bindings, but the actual implementation can be found in this folder and in this folder. For example, if you open this folder, the source, and here's the actual Rust implementation. If you open this file, this is the actual implementation. For example, this create function. The Masked Authenticated Messaging demo works as follows. There are two roles, the data publisher and the data receiver. The data publisher publishes sensor data, for example, every 15 seconds to the Tangle. The sensor data looks like this. The data is a random number between 10 and 99, and the current date time. This data is published on the Tangle. To receive the sensor data from the Tangle, the data receiver needs the root and a side key. The side key is only needed if you select the restricted mode. Now let's start the demonstration. This is the Google Chrome browser. I have opened two tabs. Both tabs open the same Masked Authenticated Messaging demo. In this tab, I have selected Data Publisher. I have selected this mainnet endpoint. I have selected this option to generate a random seed automatically. I have selected security level 2. There are 3 channel modes: public, private, and restricted. For now, let's select public. I want to display message logging in the console. Select yes. And I want to publish the data every 15 seconds to the Tangle. Open the console window. Press the button Start Publishing Data. Press the Stop Publishing Data button. If you look at the time, the data is not displayed in the correct order. This is caused because the data is asynchronously displayed on the screen. But the data is correctly stored on the Tangle in the correct order. Let's copy this root. Let's go to the other tab. Instead of Data Publisher, select Data Receiver. I'm selecting the same end node. I'm selecting the same channel mode, public. I'm not interested in message logging, and I'm pasting the root. Press the button Start Receiving Data. As you can see, it retrieves the data from the Tangle in the correct order. The data starts with 98, and that is the correct one, 98. In the console window, you will see JSON messages. Let's copy the first JSON message. This is the first JSON message. In the next slides, I will discuss these fields. But first, I will show you how to get this JSON message. When you call the mem.create method, it will return this message object. For this tutorial, I am calling this message object a MEM object to avoid confusion. Now let's discuss each of these fields. Side key. In restricted mode, the message is encrypted by the side key. To decrypt, use the same side key. The side key is used to encrypt and decrypt the message. The side key is required when using the restricted mode. Here is a very simplistic explanation how the side key is used. To encrypt your message, you need the side key and the root, and you will get your encrypted message. To decrypt your message, you need the encrypted message, the side key and the root to get your original message back. This payload is the same as this payload. The side key is not only used to encrypt the message, but it is also used to encrypt the nonce, the signature, the number of siblings, and the siblings. This will be explained in detail in IOTA tutorial 20. This message consists of the payload and the next root. The next root is the reference to the next message in the message stream. This payload contains the actual sensor data converted to tries. This is our actual sensor data converted to tries. Mode. There are 3 channel modes. The public mode, where anyone has access to the message. The private mode, only the publisher has access to the message. And the restricted mode, anyone with a side key has access to the message. The publisher publishes messages using the root. The publisher can choose the following channel modes. The public mode, where address is the same as the root. Messages can be unwrapped by anybody using the address. The private mode, where the address is the hash of the root. Messages can only be unwrapped if you have the right root and the root can't be deducted from the address due to the hash. And finally, the restricted mode, where the address is the hash of the root. Messages can only be unwrapped if you have the right root and the side key. This is the public mode. Here are 3 messages. Address 1 has address ABC. To get the next message in the message chain, you always need the root. In public mode, the address is the same as the root. Important to remember is to fill the payload, you always need the root. I have included this slide to give you a better understanding why the root is needed to fill the payload. This is a sponge construction. We already know that the side key is used to encrypt the message. But the root is also used to encrypt the message as indicated here. This drawing will be explained in detail in IOTA tutorial 20. To fill this payload, you need the root. To fill this payload, you need the root. If you stumble across address TTP, the payload can be filled because the root is the same as the address. I have copied all the JSON messages from our demonstration. As you can see over here, we are using the public mode. If you look at these 2 lines, the root is the same as the address. This is our next root, meaning this is the reference to our next message. This is our next message. As you can see, G and F is the same as this address, G and F, and the root and address are the same. This is the next root to the next message, XB9, and you can see this is the address XB9. The address is the same as the root. Now let's look at the private mode. The address is not the same as the root. This address is the hash of the root. To get the next message, we need to hash the next root value to get the address, as mentioned over here. If you stumble across address RRE, this payload cannot be filled because the root is unknown, because the address is the hash of the root and not the other way around. And the hash is a one-way function. I have created several examples for different situations. Each example has 2 links. One link will show you the MEM objects. The other link will show you the corresponding transaction objects. And here are other examples. Let's go to MEM example 2, where security level is 2 and the channel mode is private. And let's open this link. As you can see, the root and the address are not the same. The address is the hash of the root. The last channel mode is the restricted mode. The restricted mode is the same as the private mode, but you also need the side key. The side key is used to encrypt the payload, but is also used to decrypt the payload. The root and the address are not the same. The address is the hash of the root. To find the address of the next message, you need to hash the next root, as indicated here. If you stumble across address RRE, the payload cannot be filled because the root and the side key are unknown. Let's go to MEM example 3, where security level is 2 and the channel mode is restricted. This is the side key, my secret. Let's open this link. This is the link opened. As you can see, this is the restricted mode. This is the side key, my secret, but converted into tries. As you can see, the root and the address are not the same. The address is the hash of the root. Next root. To access the next message in the message chain, use the next root. In private and restricted mode, the next address is calculated as follows. Address is the hash of the next root. In public mode, the address is the next root. Let's see how the root and next root is calculated. We start with the seed. Key X number is an integer starting from 0 till this large number. starting from 0, 1, 2, 3, 4, 5, etc. And this is our security level, 1, 2, or 3. With these three values, we can calculate the key. The key is the private key. So for key index 0, this is its private key. For key index 1, this is its private key. For key index 2, this is private key, etc. For each key, we can calculate its corresponding address. This is address 0 for key index 0. This is address 1 for key index 1. This is address 2 for key index 2, etc. As a reminder, this is how a key looks like. Each square is a segment consisting of 81 tries, and this is the procedure to calculate an address. In the Merkle tree, each data is hashed first, as explained in IOTA tutorial 18. This data is hashed first. This node represents a leaf. This Merkle tree consists only of one node, meaning this leaf and the Merkle root are the same. In this example, address 1 is hashed, address 2 is hashed. These are the leaves of the Merkle tree. This Merkle tree consists of 3 nodes, of which this is its Merkle root. In this example, these are the leaves of the Merkle tree, and this is its Merkle root. This Merkle root is called root. This Merkle root is called root. This Merkle root is called root, etc. Each of these roots represents an address where a message can be attached to. A message can be attached to this root. This is the next root of the message chain, RST, referring to RST, that is this root. This is the next root of the message chain, CDA, root CDA. This is the next root of the message chain, HRT, referring to this root, HRT. If you use this Masked Authenticated Messaging demo, each Merkle tree consists only of one node, as shown here. This payload is attached to a Merkle tree consisting of one node. This payload is attached to a Merkle tree consisting of one node. This payload is attached to a Merkle tree consisting of one node, etc. Security. You can choose between security level 1, 2, or 3. Start. In the message chain, the Merkle tree uses the same seed. The leaf in each Merkle tree is only used once, and each leaf has a corresponding key index number. The leaf is calculated by hashing the address. Start refers to the first leaf key index number in the Merkle tree. Let's assume we have this situation. This Merkle tree has one leaf. This leaf has key index number 0. So start has value 0. This Merkle tree has 2 leaves. The first leaf has key index number 1, so start has value 1. This Merkle tree has 4 leaves. The first leaf has key index number 3, thus start has value 3. This Merkle tree has 8 leaves. This is its first leaf. This leaf has key index number 7, thus start has value 7. Count the number of leaves in the Merkle tree. This Merkle tree has only one leaf, so count has the value 1. This Merkle tree has 2 leaves, so count has the value 2. This Merkle tree has 4 leaves, so the count has value 4. This Merkle tree has 8 leaves, so the count has value 8. Next count. When a message is created, always 2 Merkle trees are created. The current Merkle tree and the next Merkle tree. Next count is the number of keys or leaves used in the next Merkle tree. If we start with this Merkle tree, its next Merkle tree is this Merkle tree. This Merkle tree has 2 leaves, so the next count is 2. If we start with this Merkle tree, the next Merkle tree is this Merkle tree, which has 4 leaves, so the next count is 4. If we start with this Merkle tree, the next Merkle tree has 8 leaves. Next count will be 8. Index. Within the Merkle tree, the index number is used to process each leaf. If we look at this Merkle tree, these are its leaves. The first leaf has index number 0, 1, 2, 3, 4, 5, 6, 7. The index number is used to process each leaf sequentially. Please note the index number has no relationship with the key index number. Seed. In the message chain, the Merkle trees uses the same seed. Payload. Also called masked payload. This payload consists of the actual message, for example sensor data, signature and other information. In restricted mode, the actual message and other information are encrypted with the side key. This is referred to as payload or masked payload. This message contains the sensor data and the next route. In this example, the sensor data looks like this, but converted to tries. To decode the payload, go to this link and select option Decode Payload. This is our Masked Authenticated Messaging demo. Select option Decode Payload. Select this mainnet endpoint. Here's a MEM object. The mode is public. Copy this route. The channel mode is public. Paste the route. Copy the payload. Paste the payload in this field. And press the decode button. This is the decoded JSON object. If you convert this value into string, you will get this decoded payload, and here you find the next route. If you have a payload in restricted mode, you need to enter an encryption key. Route. The addresses are hashed. These hashed addresses are the leaves, and each non-leaf node is a hash of its children. This results in a single hash called the Merkle route. For example, these addresses are hashed, and these hashed addresses are the leaves. Each non-leaf node is a hash of its children. This results in a single hash called the Merkle route. Each route represents an address where a message can be attached to the Tangle. Address. The address used to attach the message to the Tangle. In private and restricted mode, the address is calculated as follows. The address is the hash of its route. In public mode, the address is the route. If you want to see where the address is calculated, go to this link and search for this function. If the channel mode is public, then address is same as the route. If the channel mode is private or restricted, the address is the hash of its route. Please note, this address and this address is not calculated the same way as calculating the address for a normal transaction. This is the link to the Masked Authenticated Messaging demo. If you want to know how the Masked Authenticated Messaging demo is coded, I have extracted the relevant JavaScript code from this HTML file and put them in two separate files. This file is for publishing data to the Tangle. This file is for receiving data from the Tangle. This is the file for publishing data to the Tangle. The code starts here. I'm not going to discuss this code. For developers, it should be easy to understand. I have also included a lot of comments. But here are two pieces of information which developers might find useful. The first piece of information is this. If you follow this code and read this comment, what is this root Merkle variable, or root branch variable, or root siblings variable? I have created a slide. Go to IOTA tutorial 19 and search for slide #A. This is slide #A. The variable root_Merkle refers to the Merkle root. The variable root_branch refers to this path, meaning if this is your leaf, then the path from your leaf to the root is called the root branch. And what do we mean with root siblings? If you take the root branch as your reference, then the sibling of this node is your root sibling. The sibling of this node is called your root sibling. The sibling of this node is called your root sibling. The sibling of this root is called your root sibling. If you take this root branch as your reference, then these blue nodes are your root siblings. The next piece of information which needs further clarification is the following. When you create a transaction bundle, see hashtag E. This is hashtag E. The MEM library creates the masked payload and calls the IOTA.API.sendTransfer function. The sendTransfer function in turn calls the IOTA.API.prepareTransfers function, which divides the masked payload in smaller parts. Each part size will be 2187 tries, representing a signature message fragment. The last part will be padded with 9s to make its size 2187 tries. A transaction object is created for each part. The transaction objects together forms a transaction bundle, as indicated here. If you go to example 1 and open both links, I've opened both links each in a separate tab. This is the MEM object, and this is the corresponding transaction bundle belonging to this MEM object. If you copy this signature fragment, and this signature fragment, and concatenate it to one single string, you will get this payload. That is what I'm trying to explain in this slide. As you can see, you still need to confirm 2 transactions. Thanks for watching. I hope you enjoyed the video. Please hit the like button and don't forget to subscribe. If you have questions, leave your comments below. I'll do my best to answer them.